are taking physics 2b or 4b, you can easily calculate for protons to be traveling at this speed, bending them in this circle or 7-mile-long tunnel, you need to provide very strong magnetic fields, 9 Tesla. And this can only be done using superconducting magnets. So the Large Hadron Collider is and will remain as the energy frontier for this new physics discovery until at least 2030, and perhaps much longer than that. So as physicists, we are extremely lucky we are able to witness, we can participate in this great project. So this is a 70-mile-long tunnel, and then the protons are made to collide in those interacting regions. And ATLAS and CMS are the flagship experiments designed to search for new physics like Higgs and other new physics beyond the current physics framework. And if we zoom into this interactive region, we'll see detectors. So this collaboration consists of about 3,000 physicists from 38 countries, and among them, about 500 physicists are from about 40 universities or national labs in the US. It includes 4 national labs in the US, Argonne National Lab, Colloquium National Lab, Lawrence Berkeley National Lab, and Stanford Media Accelerator Center. They also include quite a few of the top research universities. At Fresno State, we were admitted to ATLAS in 2007, and among all the 23 CSU campuses, we are only one on ATLAS and CMS. So this provides an outstanding opportunity for faculty and students to work with our programs. So in order to provide this outstanding opportunity to a wider CSU community, we have been building up the CSU Nuclear and Particle Physics Consortium, and 30 other campuses have joined with Fresno State and Silicon. And since 2008, we have sent 19 students, 30 of them are from Fresno State, but also includes 6 from other campuses of Long Beach, Mona, and Sacramento, to work at CERN at least one summit since 2008. And our program has received very strong support from our college, the provost and Office of Research and Sponsored Programs. In addition, our college also we receive 15K per year from our college and another 10K from instructionally related activities, which allows us to send our students to work at CERN during summer. And those strong internal support is essential in landing 3 NSF grants since 2009, with a total of about 1.6 million, with significant influence. In addition, because CERN invested more than $10 million on Large Hadron Collider ATLAS, so they charge a membership fee for every physicist working on ATLAS. And this membership fee has been about 17K per year. And US Department of Energy and NSF have been paying our membership fee for us to CERN. This has been about 50K per year for the past few years. So during since 2008, 13 Fresno State students have worked at CERN one summer. Quite a few of them they have worked all night during the 3 times at CERN. And they work on a variety of projects, architecture and simulation, software, and physics. And thanks for the funding from our college and the IRA, this allows us to follow students to work at CERN. And these local news media all reported our students' activities at CERN. So those are the photos of our 2 postdocs stationed at CERN, also with the students in 2010 at CERN, 2011, and also 2012. Our students' work at CERN were also appreciated by our ATLAS colleagues. For instance, James McDougall, he worked with physicists from Stanford Media Accelerator Center, and they claim he is the best young student they ever worked with, including students from SLAB and Stanford. And also Sarah from Long Beach, she received about $8,000 from NSF for outstanding work in promoting science and physics to the public. More information about our ATLAS program and students' research projects can be found on my webpage. So this is ATLAS detector. So proton comes in, it's traveling So while we have those are the building blocks of the universe, the three generations of quarks and leptons, but that's not what we see in our detector, because many of those heavy quarks and leptons are now stable. So once they're produced, it decays into other particles, novel particles like photons, electrons, gluons, ions. So we have to so all the signature, they are all electrons, charged particles coming from those decays. So we have to be able, we need to be able to identify what they are before we can tell where they come from. So that's the challenge for the detector. So the particles are detected based on the interaction with the, so you can picture the detector as many layers of onions. And then the charged particles, the different type of particles go through the detector to have different interactions. And based on their trajectory and interaction with the different layers of the detector, they have different signatures. And based on the signature, we all should be able to tell what those particles are. And that's the first step before we can tell, reconstruct like particles of Higgs particles. Because they all have, that's the final state particles we detect. And also by providing a magnetic field, the charged particle will bend in magnetic field. So by measuring the curvature of those trajectories with these tracking devices, and we'll be able to measure the momentum. So we measure the momentum position, the particles decay, and those are the what we practice. So we're trying to measure those everything as precisely as possible. So that's the introduction, and then I'll So James, he worked at CERN this past summer because he made a very visible and significant contribution to the single detector. Because CERN wanted him to go back to CERN. So they paid his airfare, hotel, and salary to return to CERN in September last month. So he'll work there for another 3 months. So he's taking this methodology. So those are the slides he sent me just yesterday. So he's been working on the alignment project for a single detector. That's something I'll describe prior to the slides. So as the inner detector, that's the closest. So this is where the small Big Bang happens. The inner detector is the closest to where the small Big Bang happens. And that's the most sophisticated detector. You can imagine all particles are coming from the small Big Bang. So solenoid particles comes out. So this is the first layer, first layers of detectors we want to measure all the particles comes out. So those measurements of new detector is the most important in measuring everything comes from the small Big Bang. So this is what happens in small Big Bang. So the dimension is roughly 3 millimeters. And we can tell, because the precision of the new detector, we can reconstruct all the particles comes out. So you can see where hundreds of particles comes out. But if you look closely, we have 25 vertices. So we have 25 particles that are not stable, so they decays into other particles. So we can figure out there are 25 of them with one condition. And the precision for the vortex is roughly like microns. And then we can, based on the precision tracking, so we can reconstruct, for instance, this is the ASUS data measuring Z to mu plus mu minus. Z boson decays into mu plus mu minus. And because it's the Z mass is 90 GeV, so we observe a very clear peak. And the narrower the peak, the better the resolution. And the performance of the detector is crucial, so we have good performance so we can tell signal from backgrounds. And with this capability, this is our simulation on Higgs to 4 leptons, 4 muons. So we can see they have a very clean peak. So the tracking of the detector is crucial. And this is ASUS data for the Higgs to 4 lepton decay channel. And this is the small measure is precise. So we have resolutions in terms of in order of like 10 microns. So the project James worked on is called FSI, frequency standard uniformity. And this is using the laser technique. They are measuring the alignments of the unit detector to make sure everything is stable, and then report the alignments to measure the internal alignments function time. So they measure the length, some known points, and then check so they can achieve like micron resolutions. And then, for instance, the environment changes. For instance, during turn on the cooling system on and off, and then they'll make the unit detector in the size of like 2 meters for change. So we have to have very precise alignments and calibration of it. So this FSI project to monitor the stability of the system all the time, so we can have reliable tracking. And this is done using 842 grid lines. You can see those are the alignments. So I'm measuring the distance among all the positions and checking them, make sure everything is largely exposed to them. And this is using the laser system, using all the final system. And then during the summer, James Angulo, we found the system was not reliable. And he said, so James figured out what was wrong with the system. So he proposed an upgrade. And this upgrade has been going on since summer. And so this is the curve after the upgrades, and we see improvements in power to the parallax, so blue and red regions. And so he's heavily involved in this project, and this upgrade was essential before we can get reliable physics out of the results. So they increase this is summary of the results. We increase the power to fiber optic system, improving the signal to background ratio, and then so now we have more reliable, more stable data for more precise. This is SCT, the semiconductor tracker. This is part of the detector system, and so those are very important for the discovery of the physics, because the tracking relies on this on the performance of the system. Any questions? So Emmanuel will report on this project on the author section.
Hi, good afternoon, everyone. My name is Emmanuel Angulo. I'm a master's student here at Fresno State, and this is actually my second time going to CERN. So this is a continuation of the research that I started in the summer of 2011, and it's on the experimental analysis of the muon chambers of lattice detector. So this is the same slide as Dr. Gao had, and this blue region is the muon spectroscopy, or as Dr. Gao's analogy, the outermost part of the onion. And this is the height of a person, so you can see the scale of this detector. It's 6 stories high. So why detect muons? Why are they important? Why should we detect them? Well, they're very easy. They're very easy to detect compared to other particles. They don't have any strong interactions. They're 200 times the mass of an electron. Their lifetime lasts about 2 millionths of a second, which sounds kind of short, but it's actually the second second longest lifetime of any other particle. And we experience these muons as cosmic rays in our daily lives when they interact with our atmosphere, and we get a rate of about 1 muon per centimeter squared per second. And many of the new particles end up decaying into muons as final particles. So this diagram shows an example of a collision, and some heavy particles come out, and then to further other heavy particles, and then finally a here until mu1. So if we backtrack this and look for the missing mass, then we can calculate these other newer particles. The current detector in place uses a technology called monitor drift tubes. So you can imagine an array of tubes, very small in the millimeter scale, and they're filled with argon and carbon dioxide. So these muons come in, they ionize the gas inside the tubes, and they drift down to an electrode in the middle, and that electrode sends out a signal to the computers, which collects all these data, and you can calculate the momentum that's coming in at what angle. And there's thousands of these charged particle sensors or tubes in each one of these chambers. This is a picture of one of the larger outermost chambers for the muon spectroscopy, and this is the person doing maintenance on it. So there's some requirements for the upgrade. It has to keep the 98% efficiency. It has to improve the time resolution by a factor of 10. It has to keep the same precision tracking, both spatial and angular resolution, and it also has to reject the background, such as the cosmic rays. So what all this basically means is that they have to design a whole new detector and faster electronics. So the team that I work with is doing the micromegas chamber design. It's one of 4 Atlas teams competing to have their design integrated to the upgrade. And just to show you how ambitious this is, they already have the infrastructures of where the chambers will go once the final design is completed in 2018. Oh, and I forgot to mention the upgrade is going to increase the beam luminosity by a factor of 10, which means that the beam is more dense, it has more particles per second. So this is a couple pictures of the chambers right as they come out of the engineering department. And these are 2 different types of chambers. This is a 2x2. This is a 2-dimensional chamber, X and Y, and a 3-dimensional chamber. And here is a picture of us looking at them through a microscope in the clean room to make sure there's no debris, because those would cause bad resolutions in some of the spectrums that I'll be measuring, which I have examples of. So the design itself, it's very complicated, but I'll try to simplify it as much as possible. So it's a parallel plate chamber. It has a drift electrode up here with minus 300 volts. It has a mesh, like a cross-stitch stainless steel mesh. And then it has the strips here at the bottom. The mesh is grounded, and the strips have a positive voltage of about 600 volts. We vary this plus or minus 50 volts to check for different better performances. So the muon would come in here, and then there's our argon and carbon dioxide gas, just like the old chambers. The muon comes here, it ionizes, and then it drifts down just as before. But the biggest part here, the biggest difference, is this mesh that separates 2 potential differences on the voltage from the top and the bottom. So this is about 5 millimeters apart, and with 300 volts difference, you get about 40,000 volts of potential difference per centimeter. And here, there's a 600 volts difference and a gap of 128 microns. So you get about 4 million volts per centimeter. So this makes for a higher rapidity as the charge goes from here to here. So the lab environment, this is a picture of the outside of the lab. It has some radiation signs, some food drinking, a siren. They're kind of intimidating, right? But as you walk in, it's kind of stress-free. They actually let you work at your own pace. I work in this corner back here with a bunch of electronics and very repeatedly designed programs. The three bottom pictures is they have an annual test being run. So all the tests that we do in the labs, they want to replicate here with the actual test beam. They split up the beam, and we go down to the cavern, and they have this the beam coming out here, and we align all the chambers like this. So we we test all these different chambers simultaneously. This is the chamber setups in the lab. This is one of the chambers here. It has a little platform that goes up and down left and right. And there's an X-ray gun that shoots out photons, which has similar properties to muons. So we can use this as we can shoot out muons at an efficient rate. And this is a zoomed out picture, and you can see the copper shielding for our safety, for safety purposes, for radiation, to wipe out radiation. And this is a picture of the electronics that we use for it. So an overview of the lab tests that I did, I measured 8 different chambers. They were called the T-series chambers. A little bit different design that I worked with last year. I will go over just one of the chambers. And then I also examined how well these regions work. And towards the end, they had me test out 2 reference chambers from the test beam that were getting some anomalies on some of the parameters. So I had to duplicate these in the lab, which I did, and I found out why they were acting that way, which I don't have here either, but because of time restrictions. But here's a picture of a chamber, and this is the region. This dark brown region is the region that we shoot the photons in. So I made a grid. This one's 90 positions. So I would align the X-ray to the center of each of these squares to take the spectrums on the different regions. I also optimized operating conditions, made sure everything was consistent for each measurement. For example, I found the best high voltage on the drift and the strips to use to get the best resolution. We used 2 different tensions on the mesh, which I'll explain in the next slide. And my data taking and analysis had to be consistent with every chamber and get good results, unbiased results. Here's an example of the photon spectrums measured from the X-ray gun. The plot here on the left, well, first of all, the y-axis is the number of counts, or the number of events that are happening with the X-rays that I'm shooting in. And here is it's a 5-volt scale, but it's changed from 0 to 1,000. So 200 would represent reading of 1 volt of charge. So we connected all the strips together, and we would get a total charge depending on where we would shoot these photons. For example, here I was getting a reading about 300, 1.5 volts of charge, and this is the spectrum that we expect for a photon. And this is a bad spectrum. This one has a higher signal or a higher peak width halfway up. And what this is saying is just saying that there's something wrong going on here. We can't tell what exactly is going on. It could either be because of debris, some dust debris. It could be because the strips are touching each other. It could be because of bad design from the engineering department. That part I can't figure out. We just say, okay, these regions are bad, and send it back to the engineering department. So last year, I took the peak positions and plotted them for each of these, the mapping here, for the square that I showed earlier. And depending on how much charge from the peak, from the peak number, the light ones are where you have low charge, and then the darker ones where it was high charge. And this one is a chamber with a high tension mesh. So they had a frame on the mesh, and they stretched it out to high tensions, and it wasn't permanently attached to the chamber. So when I turned on the high voltage, the electrostatic force brought that down. but because it was stretched out, it was a little bit farther from the strip, so we got this low charge on the edges. And then I sent it back to the engineering department, and they changed it to a lower tension. So now we have more of a sag to the mesh, and it was closer, so it got a higher charge. So this one looks a lot better. So something new that I thought of this summer, I wanted to get more information out of these visual plots. So I started thinking, well, what else can I do instead of color coding them and just putting them in the I experimented. I said, well, what if I got all of the spectrums, the actual spectrums that I had, and made them smaller and started putting them in these squares, in these positions. I wonder what would happen. So I did that, and I got this pattern, this really interesting looking patterns to my colleagues. They actually got a lot more information than what I was able to get. They can see exactly where there was a more sag on the mesh, and they can see some kind of anomalous region here. And in this region, you can see that not only that the peak position is good for this area, but also that the resolution on the spectrum was good too. So you got two informations, or more information from each of these plots. And this is a chamber with the old style with a permanent fixed mesh, and this is what we're actually supposed to expect to get. So all of these peaks are about the same position. They have a good spectrum. The sigmas are about the same for all of them. So in summary, all of the lab test results match the results for the test we run. This new visual layout for the uniformity test is continued to be used by the micromegas team, and I also trained 3 other students to continue doing these measurements before I left. I left CERN on my last days, and I participated in 3 of the test runs in the cavern and gave 4 talks for the Atlas micromegas meetings, and this research will be incorporated into my thesis. These are some pictures of some of the more recreational stuff that I did, showing the culture. This is Ari and I went to see the Dark Knight Rising there, so it's pretty popular over there too. This is a picture by the lake in Geneva. On the weekends they open up a pier where you can go out and swim in it. These 2 pictures are for the Geneva Festival. On the last day of the festival, they have this big fireworks show, and the day before that, they have a big bonfire with concerts, music, and background. This is the lake parade. This is us as a group getting there early, getting ready for the lake parade, and this is while the buses. These buses all have different types of music going around the lake. Music from all over the world, so they're big on music. And that's my talk. Thank you very much.
Any questions for Emmanuel?
Hello everybody, my name is Gonzalez. I am an undergraduate physics student here at Fresno State, and this was my first summer at CERN. So this summer I worked also on the Atlas experiment along with Emmanuel with the micromegas team. Now the chambers that Emmanuel was talking about that he did tests on were about 10 centimeters by 10 centimeters. So they were small chambers. essential to see how well they work. This design works and several different designs work. However, the minimal size for the chambers when they're implemented into the Atlas experiment will be at least 1 meter by 1 meter. Now, micromegas of this size have never been built. So I was supposed to answer the question, can we produce some boards that can be used for this? So my responsibility was to test how well these boards were manufactured in order to use them for these micromegas chambers. Now, it's that they wonder if boards of this size are reliable, if they'll meet specifications, and if they'll work very well with this design. So here you see the size of one of these boards, 2 meters in length and 60 centimeters in width. So these companies were given certain specifications to how to design these boards. They were told how many strips they're supposed to have running along the length of the board. There you have 1,250 copper strips running along the length of the board. They also wanted a pitch of 400 micrometers. So every one of these strips are supposed to be separated by 400 micrometers. And the pitch would be the distance from the one copper edge to the next copper edge. And also, they were given the distances between the fiducial marks on the boards and the fiducial to strip marks on the boards. My job was to make sure that they met these specifications for these boards. So in order to get the strip pitch of these boards, the first instrument I used was a laser interferometer. Now this is a laser that travels along a track, computer controlled, and would take measurements at different parts of along the length of this board. Here you can see the laser head right there, and I also have a video showing it working. So we have the laser right here. It goes onto the board and shines out, and there's a it gets scanned into there, so it's able to tell how far away it is from the board. So here you have it shining onto the board itself. Now, scans of this type would take rather long, about an hour and a half. And here you can see how long it takes to go between the copper strips and the gaps. So every time you see the laser shining through, it's in between a gap between copper strips. So it's shining through the printed circuit board. When you don't see it, it's on a copper strip. So I did full scans like this along the board, and I would start here at the center and then get 2 more up on the top and then 2 more on the bottom. Full scans would produce some data files that were rather large, about 60 to 70,000 sets of measurements. Those were then plotted, and you would get this different types of plots. Here you see one with a curve. Now this resulted from the board, a little bend of the board, and that was expected. PCBs aren't rigid, they're quite flexible. And when they were mounted onto this rack, it was seen that there was still a bit of a bend of the board. However, this would not damage any of the results I would get. The measurements would still be fine. If you zoom into a certain region of these measurements, you still see distinguishable peaks and valleys. These can be used to find the pitch between the strips of the boards. At this point, I had quite a bit of data to look at, a lot of measurements to do, and several more boards to do. I wouldn't be able to finish it within the amount of time that was given, the 10 weeks I was there for CERN. So luckily, the supervisor for the group gave me 2 summer students to assist me. Now, I was able to use them in any way I wanted to, so I decided to have them do the programming to look at my data to find this pitch. Here you have Claudio, he was from Italy, and Despina, she was from Greece, just to show some diversity of how many different people I worked there while at CERN. And they produced very promising results. Here we have the mean pitch for just one scan along one board, and we get that 400 micrometers pitch. It's displayed there in the blue. We have the red is a Gaussian fit for it to show how well the data was, and we had a standard deviation of about 6 micrometers. So we have very good results. The next part was to see how well these measurements of the fiducial marks and the copper strips were between one another. And we also wanted to see the overall width of these copper strips, how far away one copper strip is from the very last copper strip. Here you can see the traveling microscope with a board on its table. Weights were placed on this because these readings were a bit more sensitive. Readings with a longer length would be a bit different than the shorter measurement readings. So we want to get rid of that bend. We want to make sure it doesn't have that bend, otherwise it would have very different results. Here you see a fiducial mark as seen through the microscope and the copper strips. Now, the results from the distances from the copper strips and fiducial marks were as expected. They did meet specifications. But there was another thing that we looked at, and that was the overall width of these copper strips from one point to another. And we did readings at different positions along the length of the board. So we would see how well they were manufactured to make sure that they are uniform with one another and that the copper strips do not bend in any way. And here we have a graph of them plotted against one another. Each one of these lines is a different printed circuit board. Now we want them to overlap and we want them to be as straight as possible. However, these boards from Italy weren't that straight. However, boards that came from the United States at Nevada were a bit more promising. As you can see, as they are appearing, you see that they are stacked on top of each other. This is good. We want boards that are uniform with one another. And you can see that they're also quite straight at certain parts, here and here. So that wasn't too bad. We had a difference of about 40 micrometers, which is within expected values, except for the very end of the board, we did get a bit of a staggering, something a bit different, but it was fine. It wasn't too bad that we wouldn't be able to use a board of this design. And lastly, the larger boards that came from the United States, here in Nevada, have similar results. You see that each board, as back against one another, they are on top of each other. And even though they're not that straight, differences among them are within 30 micrometers, right in the central region of the boards. So that in itself was good too for the boards. We were expecting something like this, and this is what we were looking for, something with small differences within the boards. So the conclusion from all these measurements was we did get a pitch of 400 micrometers. We did get consistent readings within small measurements of the fiducial marks and the fiducial copper strips. And we did get good values for the boards made here in the United States. So the USA did make better boards than Italy. And we also see that just with these standard manufacturing procedures, they can still produce fairly well boards. So